Dear ladies and gentlemen, welcome to One SciTech, One Future series of Why Not. Today is a special of Hong Kong SciTech Pioneers Award and sharing session, MIH Talk, Beyond the Feasible. So you may wonder what MIH means. So let's have a look.
The word revolution used to mean rotation. Copernicus indicated that the Earth was rotating and that the Earth was not the center of the universe, the Sun was. Copernicus was the first person who started the modern scientific revolution. From Galileo Galilei's free-falling experiment to Newtonian mechanics, predecessors built the framework of modern science. And then science empowers human beings to the modern and to the future. But we are still facing many challenges. 40% of COVID survivors suffered from long-term after effects. 50% of global students are unable to learn daily and have no aspiration of digital literacy. 130 million people will be pushed into poverty by climate change. In every era, there are key figures leading the development of SciTech, helping human beings get out of the predicament and move towards a better future. Who will be the next pioneer? You. The best way to predict the future is to create it. The MIH Club features a smart community giving circle which consists of professional scientists, entrepreneurs, and talents like you from various professional fields. Let's gather your wisdom and talents to jointly promote the development of human society. Come and join us to be an advocate and a promoter to transform our future with SciTech. Together, we build a sparkling and brighter future. Let's make it happen.
So welcome. I'm Yan, Strategy and Project Director at Why Not. So one of the top priorities of Why Not is to make the knowledge of SciTech accessible to everyone. So today we have Professor Li, an astrophysicist from Chinese University of Hong Kong. So it's going to be a very exciting talk because he's going to tell us his grand mission to build the first Hong Kong astronomical camera. So let's get inspired and find out more about him in the following video. Thank you.
Astronomy is one of the oldest sciences of mankind. Humans have always had a deep fascination with the relationship between stars and humans, a desire to understand who we are and where we come from. In the year 1054, Chinese astronomers in the Song dynasty observed a supernova explosion and recorded it. It became the earliest record of supernova by human beings. Then, in 1932, radio engineer Carl Jansky from Bell Telephone Laboratories accidentally discovered that objects in space emit radio waves. Since then, pioneers with even more complex instruments, like a submillimeter, have pushed science forward, bringing humans beyond the visible. With this type of submillimeter telescope, humans were able to make astonishing discoveries, from testing Einstein's theory of general relativity in environments where extreme gravity exists to probing the physics around black holes with unprecedented detail. Our speaker today, Professor Li, from the Chinese University of Hong Kong, who leads the Stardust journey in the stellar nativity, will explain to us the beauty of the universe and the importance of submillimeter astronomy to Hong Kong's space science development.
Now, welcome Professor Li on stage, and you will have the time to present. Thank you.
Ladies and gentlemen, good afternoon. I'm here to tell you a small story about the first astronomical camera we're going to build here in Hong Kong, now under construction in CHK. So I will start from why, what's the motivation, and what exactly do I mean in astronomical camera. And I'll spend a short time to tell you how exactly we can make this happen. Okay. So why we need a camera? And the answer is very simple, because our human being eye cannot see much. You can see me now, of course. You can watch TV. You can enjoy the beautiful scenery in Sai Kung. But when you really want to know about something, the universe, for example, you need to know much more. And you cannot depend on your eye. And you can easily feel what I'm talking about, given the opportunity of the last few years, right? We see this a lot in the past few years. You can see me, but you cannot see my temperature. But an infrared camera can easily tell your body temperature. Later, I will illustrate a little bit how this is possible. But before then, I want to show you a series of discovery of the universe that we found depends on various of cameras. We start from the Earth, and we're gradually zooming out. Okay, hold on your seat. So here's the Earth, this is zooming out. So we see the moon, of course, and our neighbor planet, the asteroid. Okay. Venus, Mars, Jupiter, Saturn, Neptune. And we see the solar system like a disk. And we're actually in the center of a cloud. For cloud, I mean a dense group of gas. And near stars, about 4 light years from us, and the distribution of the stars are kind of clustered, so they are not very uniform, and then distributed in the spiral arm of the Milky Way. The Milky Way have neighbors, and neighbors have more neighbors, so cluster of galaxies seems to be permeated everywhere in the universe and form a web-like structure called cosmic web. And that's pretty much we know about the universe. And most of the structures that I just show you are not visible. And it depends on various type of cameras to let us show, to see these structures. Okay, so hope you're not feeling dizzy. But this is a very short summary of all the structure I just showed. We're in the center, the solar system, and we are in the middle of the cloud, and the cloud are distributed along the spiral arm. And we have many neighbors. The neighbors, with the more neighbors, become clusters of galaxies. And this is ubiquitous in the universe, form this web kind of structure. And I have got some note here, stars, molecular cloud, Milky Way, and these are the topic that currently Hong Kong astronomers are studying. Okay. So we need cameras, otherwise none of this is possible, right? Okay, now is what I promised, right? Why the infrared camera can tell us body temperature. Let's start from an even easier case, the sun. The surface temperature of the sun is about 6,000 degrees Celsius. The one important law of physics is that no matter the composition of the material, when they achieve some certain temperature, they all give very similar radiations. For example, the sun is 6,000 degrees Celsius. So he will radiate this spectrum, the yellow spectrum. And for spectrum, I mean he radiates all kinds of radiation, different wavelengths. The rainbow wavelengths we're all very familiar with, and they all have relative strengths. So anything reach 6,000 degrees Celsius, they will more or less give the same type of radiation. Okay, we can see the rainbow colors, but that doesn't mean that the sun only radiates rainbow radiations. It radiates much more than a rainbow. Just our human beings are limited to only see this range of the radiation. Okay? And let's go to other temperature, like you and me. We got about 37 degrees Celsius, and you and me are also radiate. We are glowing. Just we won't be able to see it because our eyes can only see here, and our radiation, our glowing, is mainly follow this red spectrum. It's in the infrared range. So we should be happy that we cannot see our own glowing. Otherwise, you'll see your nose all the time. Right? Okay. So you got 37 degrees, you got one spectrum. You got 40 degrees, you got slightly different spectrum. This is how those infrared cameras can judge our body temperature. Okay. So we all know that the temperature at the night will be colder than in the morning. So imagine the majority part of the universe, when the starlight cannot shine on, it will be very cold. So a big portion of the universe will have very low temperature, minus 200 to minus 270 degrees Celsius. And for structures this cold, they will glow in even longer wavelengths. The spectrum will be like here. So it's between 0.1 millimeter to 1 millimeter. And we call it sub-millimeter. And that's why today we want to talk about sub-millimeter telescope or camera, because the majority of the universe is so cold. They won't glow in the radiation that can be seen by naked eye. In this slide, I try to put the sub-millimeter in the context of other radiations that you probably feel more familiar with. Okay, so sub-millimeter is here, and if we go even longer wavelengths, it's microwave. It's probably many of you warming up your dinner, right? And if we go even longer, it's radio frequency. This is how we communicate. We go shorter, infrared. This is how you and me glow, infrared. Then optical radiation, ultraviolet, and X-rays. So we are here. It's today's main topic. Now, suppose we got this camera already, sub-millimeter camera, just like you want to use the infrared camera to see human body temperature. So what should we look at when we take a photo with this camera on the sky? Let's start with some target that everybody is familiar with, Orion. Many of us know this, right? The shoulders, neck with the belt, the sword of the hunter, right, in the skirt. So if you look at this photo, which you can have with your naked eye, you might think that the stars are quite lonely. Right? They have long distance between each other, and it's quite empty between stars. But when you take a photo of Orion with sub-millimeter camera, Orion will look like this. So suddenly, the empty space all glowing up, glowing at sub-millimeter. So this photo tells that we got stuff permeate almost everywhere surrounding Orion. And the stuff, for this case, are very cold dust grains. Okay. So by studying their spectrums, we can know their temperature, and by how much of its radiation coming from these regions, we can even judge the mass of these materials. So it turns out this cold stuff got the mass about 1 million times of the mass in the stars. So majority of the mass in our Milky Way are actually in these cold stuffs, instead of in the stars that can be seen by us. Okay. Then we won't be satisfied with just Orion, right? We can take a panorama photo of the entire Milky Way. It will look like this, okay? So this is the view you can get from Cyclone in the summer night with very nice cameras exposure for a long time. And you will see the milky part, which are the stars, of course. And the dark part, again, you might think they're empty. But if you look at their corresponding position from these sub-millimeter camera photos, you will see that they are not empty. Let's take this one example. You see it's a very dark filament here. And correspondingly, in this photo here, they all glow in sub-millimeter. So again, this tells us that these dark regions are not empty, but opposite, they are the most dense regions in the Milky Way. And they are dark, not because it's empty, but they are so dense, so they can block all the background starlight. That's why it turned out to be dark. Okay. And if we try really, really hard, we can know more with this camera. Besides the mass, the temperature, we can even see velocity. So those clouds are not standing still. They are very violently turbulent. So all the motion here are actually supersonic, faster than any jet flight on Earth. Very fast, very violent. And you try even harder, we can even see magnetic field of this molecular cloud. You might wonder, why should we care? Well, why should we care about astronomy anyway? It's curiosity. So these are the birthplace of the stars. So we are thinking, this turbulence, magnetic field might tell us how stars are formed in these regions. But this is just biased to my personal interest. This is how my group, using various kinds of a submillimeter camera to study. We study star formation. But this is not the main topic for today. Today it's for how can we generally use the submillimeter camera. Okay, so I've been in Hong Kong for almost 9 years. And since I moved here, almost every year I've been asked this question. How can you do astronomy in Hong Kong? You got laser shows at night from downtown. You got light pollution everywhere. How do you do astronomy? But after this talk, you can answer this for me, right? And because our camera looking at here, those laser shows are here, so we don't care. Our camera cannot see those laser shows, so no problem. But we have even bigger problem here. We cannot see the laser, but the problem is the water vapor in the air. So this is very informative figure. Let me show you another detail here. You see these plateaus, hills, mountains, another plateau. Right? This stands for the opacity of the atmosphere. So when it's in the plateau, it means the atmosphere is opaque. It's not transparent. For this range, for radio, we see there's no plateau, no hill, right? So it means the atmosphere is completely transparent, which is good, right? This is why we use radio to do communications. It can penetrate the air. And the visible light, good. Atmosphere is transparent. But for submillimeter, it's almost completely opaque. Due to the water vapor, so all the radiation from the stars, from those clouds, celestial objects, when they hit our atmosphere, they will be absorbed by H2O. How to solve this? You can go to space, go above all the atmosphere, but how big a telescope can you fly? And for a lot of research, we need a very big telescope to offer very high resolution. Okay? So space won't solve everything. We need big telescope on the ground. The solution is to find the driest place on the Earth. For example, the volcano of Hawaii. This is the big island of Hawaii. It's actually composed by 2 volcanoes. The volcano is above 4,000 meters high. So due to the local combination of geometry and the local climate, the winds coming from the ocean are going to climb all these high mountains. And the clouds will form before the winds can reach the mountaintop. So the mountaintop becomes very, very dry. All the clouds are below the mountaintop. So on the mountaintop, we got some transmission, maybe 20% of the submillimeter radiation from space can pass the atmosphere here. And this telescope here is 10 meter in diameter. So you're not going to be able to fly this to the space. And right at this moment, they are packing this telescope and trying to move it to Chile. And the reason is there's even dry place in Chile. In the Atacama Desert in Chile, it's the highest desert on the Earth, 5,000 meters high, and it's even drier. My experience there is we can get about half, 50% of the transmission through the atmosphere. So you see lots of big telescopes, right? This one is 12 meters in diameter. They all go to Chile because it's good weather there. So this Atacama has been gradually developing into the so-called the world capital of astronomy. But the Atacama is not the driest place on Earth. We want to try the driest place on Earth. Antarctica, right? I heard that. Yes. Exactly. Antarctica is the driest. And because it's so cold, all the water, well, not all, most of the water vapor turn into ice and fall below our feet. Right? So South Pole is the best place. But it's so hard to reach, right? And hard to build the big telescope there. So most popular place goes to Chile. So now you probably already see a big benefit for being an astronomer is, well, in case you like to travel, right? You travel a lot. We also have to be very patient because for one study, it's easy, we count time by decade. Right? One study, we have to give it a decade at least in order to see some result. And the reason is not mainly that we travel a lot, right? So spend so much time. But the reason is that, as you see, you don't get much good sight for building telescope. So you don't have much the sub-millimeter telescope. Right? And astronomers from the whole world, not from Hong Kong, have to travel. Astronomers from Germany, from US, they all have to travel to these places to get a transparent atmosphere. Right? So it takes a long time to collect the data. If you are lucky, you probably got 5 nights per year. That's when you are lucky. So imagine if your study take a month of observation. It takes you 6 years already. Right? So it's very, very time-consuming. You have to be very patient. Unless you own the camera, then you can observe whenever you want. Right? Whenever you save enough money to travel to those places, you can observe. Right? You don't have to wait, compete with others. So that's the dream we Hong Kong astronomers have, and we try to make it happen. And we collaborate with a new sub-millimeter telescope in Greenland. It's called the Greenland Telescope. It's a brand new one, and they agree to host the camera made in Hong Kong. Before I show you the detail of the camera we are building, I want to make some definition clear. So I'm talking about camera, telescope, some of you might get confused, right? But for telescope, I mean this whole set here. You got a dish and also the camera under the dish. So for the dish, I'm talking about today like 10 meters, 12 meters. The function of the dish is not too different from the lens of a regular camera. So it will concentrate the light onto the detectors, in this case the CCD, and the CCD is placed in this black box. Okay. So for the dish, the most eye-catching part of the telescope has the function of collecting the radiation and send to the camera under it. And for the cameras we're building in Hong Kong right now, is the one put under this dish. Okay. So it's comparable to this black box plus the detector array showing here. Okay. Just now, the black box is as big as myself. So it's a big box. To host a detector array, not too much compared to the regular CCD. So this detector array we are going to install. And here is the coin. So you see the detector array is not too big. Right? The reason we need such a big box to host this small array is that we need to cool this array down to minus 273 degrees Celsius. So this will be the coldest place in Hong Kong when we finish this. And when we move this to Greenland, this will be the coldest place in Greenland. And why we need temperature so low? The answer is simple. Right? When you take your body temperature, you won't take a thermometer of 50 degrees to do the job. Right? It won't work because your temperature is lower than the thermometer. They won't work. Right? You need a thermometer cooler than your object. And if you recall, our object is like minus 200 degrees Celsius, minus 270 degrees Celsius. So we need a thermometer even lower than that. Okay. And this has been supported. Very luckily, I really appreciate the support from Hong Kong government and CHK. So we will be able to construct these two parts. But this is just the start of the long journey. Right? After we construct it, so what? We need to put this onto the telescope, and we need to couple everything with the telescope. Right? So I won't be able to do this myself. So I've been recruiting my superheroes to do the job. Okay? And we call ourselves Roger. Stands for Remote Observing from Greenland. So we are Rogers. And I will use for 1 minute per person of the superheroes. I tell you what they are doing. Okay. First, Jun Kun is doing optics. So now I tell you a 12-meter dish. I tell you a coin-sized detectors. Then how to connect these two things? You need lots of other optics. Not to mention that I tell you that we can measure velocity, we can measure magnetic field. All this comes from the spatial optics. So we got the guy in charge of optics design. And of course, we got the cryogenic guys taking care of the big refrigerator. Right? And the detectors also. And each single component I'm talking about here are controlled precisely by computers. Right? So we got cryogenic, detectors, optics, and not to mention we got the telescopes. So all these components have to work completely in harmony in order to take useful data. So we need a conductor, and the conductor is our captain, Kahe, and he got all kinds of electronics and computers to try to communicate with all these components. And if these three guys did their job, you will still don't have those beautiful photos I showed you earlier. If they did their job, means that our detectors, by the way, in the background, is the same detector I showed you in the previous slides, but now I zoom in so you can see individual pixels. So if these three guys did their job well, what we got in each pixel is like, the signal will be like here. So these are voltage, well, these are detectors, right? They output voltage. So, and look at this detector, for example, it's the time. So given different time, the voltage output is like this. It's almost like a noise. It's far, far away from the beautiful photo I showed you earlier, right? The reason is because they are noise. So recall that the water vapor has taken away most of our signals. But the water did something even more nasty. It also emits submillimeter itself. So what we see here are mostly those submillimeter radiation from the water vapor. Even you go to South Pole, it's the same. The residual water vapor in our atmosphere will give the signals 100, if not 1,000 times stronger than those signals coming from thousands of light years away. Right? So we need a dedicated guy to dig those tiny signals out from this noise. Okay. So what's my job? I have to pay them and feed them, right? So let me know if you know some guy rich and interested in astronomy, right? We need support. In the last phase, if all of us doing our job, it's time to go to Greenland. And of course, we're going to take in data, do our science, but that's not the only purpose of us. Our purpose is to open this camera to all Hong Kong people. Right? You might think, how can I do with this? Yeah, lots of it you can do. Even a high school student, university students, lots of it you can do. I mean, imagine if we have our own camera, the data will flow every night. So we have a big data. So we are going to have data analysis, a workshop. So Jun Kun, that guy over there, can run the workshop and teach you, will give you, share you a piece of the data, and teach you how to do the treasure hunt. Right? Dig small signals out from the noise to see what is happening. You will be the first to see a region in the universe. Right? You will first see the signal from there. And recall that the signals are not visible. Invisible means good, means you can do anything to those signals. Here's a good example, right? Since it's not visible, you can apply all the colors based on some function you like. It gives them meaning, right? For example, here, the colors means the strength of the magnetic field. And the magnetic field also have orientations, right? So this guy did a great job here. He combined the Van Gogh idea with the data from the Milky Way magnetic field. Right? So you can run your imagination, do this kind of visualization project. And not to mention, the telescope is basically a robot. So there's lots of engineering, software, and optics that students can learn about. Okay, so this will be a big steam machine, actually. And this will be phase 3. Okay, so it's pretty much my talk. So the conclusion is, we just start a great journey to build the first Hong Kong-owned camera. Right? It's not much running in the world. Okay, so we need your brand or your support to make it happen, to put our Hong Kong on the world map of astronomy. Thank you.
We look forward in the coming future to having the first ever Hong Kong-made astronomical camera be installed in Greenland, allowing more people to see beyond the visible and help humans unlock the mystery of where we've all come from. Sub-millimeter telescopes will serve humanity into the next generation and beyond with their expanded capabilities. The seed of tomorrow's revelations is already being planted as a new age looks up at the sky and wonders. Let's make it happen.
And today I'll have some special guests I would like to introduce to you guys. And we have 2 special guests from SciTech Advisory Committee and MIH Club. So let's welcome Mr. Charles Chow, partner from Jones Day and International US law firm. Let's give him a big hand. Welcome, Charles. Thanks for coming. And then we have Mr. Michael Ho, director of our crowd, and Israeli venture capital investing in technology startups. So I would like to invite both of you to interact with Professor Li. So maybe I can start with Michael.
I was asked to ask you a question, like for your Q&A section. I think for smart people like Dr. Li, he obviously has a lot of success case to share with us. However, I think a success case is so hard to duplicate, and I think it's not so meaningful to learn from the success case. So I want to maybe listen a little bit about any failure case you have in doing all the experiment, in your such a long career.
Okay, I won't call myself a successful case, actually.
Okay.
Yeah, look at all the travel I have, and I start my PhD in a theoretical group, doing simulation, doing everything in computers. When I was young, I thought it's cool. But then at the end, I found I was locked in the basement every day, debugging. And my friends are going to Hawaii and South Pole. At some point, I fed up. So I want to do instrumentation. Right? So I do instrumentation. But then I learned that for instrumentation, again, the project, you use decade to count. I have so many ideas every day. I think if one idea takes me 10 years, how many ideas I can run? So I transfer again. I will become an observer. So I don't want to build cameras. I just want to use it. So every year I can have lots of ideas, observe different things. So I'm wandering around a lot. That's maybe why I can do all this now, but I'm the oldest associate professor in my department. So depends on how you define success, right? I don't feel I'm particular success. I'm just very passionate about the things I'm doing.
Actually, I do have an extra question.
Yeah, please go ahead. We have time.
I mean, for venture capitalists, which is myself, that I invest into quite a lot of a high-tech startup and growth stage companies. And one of the difficulties I have is that what they're doing is too advanced. I think for astronomy especially, it's really hard for you to explain to other people who have no technological background that understand how meaningful of the things that you are doing? Like, do you have such experience as well? Or like, how can you solve that?
Yes. Am I doing an okay job today? I'm confusing all of you.
I see so, everyone is awake, so it's okay.
Yeah, you're absolutely right. I also practice a lot during my 9 years in Hong Kong. I need to teach a summer course. Actually, the reason we cannot have this earlier because I have to teach the summer term. So in summer term, I teach astronomy to non-science major. And I was told by university that I'm allowed to use maths because they are non-science major. But every year at the end, I got 1 or 2 students come to me, tell me we want to transfer to physics. Last year is a student from the Department of Pharmacy. He told me I want to transfer to physics after seeing all these phenomena. Even though he's stopped by all his classmates, right? I asked him, don't do that. But they asked him, don't do that. I think because of the same reason, because I admit, lots of my friends, they cannot continue to do astronomy. They move on to industrial and making big money, right? But for the successful ones, they are doing what they love. But I think this is also one criteria, right, to select successful scientists, that you really have to be passionate enough. So I think I did okay job to convey some of this information to non-science majors people. Right? And of course, I need to improve more, of course. And I need everybody's help. Right? If you feel interesting, I'm willing to talk more with you, and maybe you can be a better communicator to transfer this information to others.
Thanks a lot. Thanks a lot.
Thank you, Michael. Thank you. So next, I would like to invite Charles on stage. If you may, please. Let's welcome Charles.
Professor Li, thank you very much for the talk. I would like to echo what Yan said. This is a really eye-opening experience for me. Because, I learned some science when I was a primary school student. I think this is a good time for me to catch up my knowledge. In fact, I have 2 questions to ask you. First of all, in terms of the advancement of science and technology, obviously, mainland China is more advanced than in Hong Kong. So for this meaningful project, is there any element that you can consider that China or the Chinese government or universities in China can take part in it to make it a great success?
Oh, definitely. And this is such a complicated machine. Right? We cannot build everything from scratch in my lab. It's just impossible. The specialty of my lab is the magnetic field machine. How can we make the detector see magnetic field? But we don't build those tiny chips in our lab. It's actually, we collaborate with the Purple Mountain Observatory in Nanjing. So they offer that chips. Not for free though, we still have to pay them.
I see.
Yes.
My second question is, well, of course this project involves a lot of funds in order to complete the whole process. So is there any element, because people talk about money, so I just wonder if from a more practical perspective, is there any element in your project that can be commercialized so that will help you to raise funds to finance the completion of the project?
Okay. I cannot immediately think out from this particular project, but I can share you a case. Yes, another of my astronomer friends who gave up. He's now opened the 5G company in Taiwan, and it's been met by President Tsai Ing-wen many times because he's so successful. But he was working with me. But now he gave up making those chips. He started making 5G testing equipment. This is one example. This is all radiations. Right? When you mastered about handling the radiations, then you can come up with an idea to make this, to make money, right? If you decide to go this way. I think it's not the problem. The basic thing is physics, right? So if you wanted for this guy, he's so successful because he knows the physics of radiation so well. So this set him different from other competitors. So I think physics, the basic things, can apply to anywhere.
Thank you very much, Professor Li.
Thank you.
Thank you, Charles. So now I would like to introduce a little bit about why lot. So let's have a look at the video.
Compared with US, mainland China and other Asian peers, even Israel, Hong Kong R&D spending remains woefully low. Hong Kong's sci-tech sector has much to catch up. Today, scientists and innovators are facing many challenges in this industry. There's a long and tedious process of public funding. Also, private investors don't have long-term vision to invest in highly skilled scientists. VC companies bet on startups that return the fund. So what can we do? Why lot is an answer. Why lot aims at making knowledge of sci-tech more accessible and approachable to everyone. We have a team of professional science advisors and seasoned professionals for proposal assessment. We believe that our 4 sci-tech pillars will be great catalysts for a better future. Our pool fund, Sci-Tech Future Fund, the first pioneering fund in Asia, leverages on the use of sandbox concept that seeks to support startups and science projects, giving room and patience for them to take trails, advocating sci-tech education, and mapping out the resource gap in Hong Kong. Under the Sci-Tech Future Fund, we particularly set up Inspire Science Grant to support science research and technology transfer. In addition to strong ties with scientists, Wylot also has close collaborations with different universities in Hong Kong and research institutions. In 2020, HKUST established the Phi Chi N Education and Research Fund to promote the future development of sci-tech and its education. And a scholarship named after Wylot Foundation was founded for encouraging and rewarding young students' outstanding academic achievements. We are Wylot. Let's make it happen.
So yes, thanks so much for watching, and let's foster sci-tech future together. So just to recap a little bit, why lot we established this sci-tech future fund. So in particular, we want to support science research, advocate sci-tech education, and map the resource gap for Hong Kong sci-tech scene. I think in particular, as you know, today's is actually part of the One Sci-Tech, One Future series, because previously we have organized a Hong Kong Sci-Tech Pioneers Award to recognize the outstanding startups as well as young scientists in Hong Kong. So we're actually bringing this scientists and startups into schools, in particularly secondary school. So I know there are a lot of different people from different walk of life. If so happen that you're interested, so please do talk to us. We're going to do this in July and August. And in particular, for primary school, we also offer co-art workshop as well. So this is also part of the One Sci-Tech, One Future series, which is supported by Innovation and Technology Commission. So please feel free to talk to us. And in particular, yes, this is our latest initiative, which is the Inspire Science Grants. And this is the first nonprofit grants in Hong Kong to support science research. And this is pretty innovative and groundbreaking, and we would like to work with young scientists as well as scientists in a more mature stage. And we love to support different kind of science research in different stages as well, from theoretical to applied, translational to even like technology transfer at the end. So, so again, if you're interested in our work, please feel free to check out our website. And thanks again so much for coming and joining us today. Thanks, Professor Li, and thanks our guests. And I wish you a great day. And last but not least, I wish you will have a good day. And if you can fill in the feedback form for us for this event, that would be awesome. And thanks again for joining, and have a great day. Thank you.